This video is to introduce the instrument control board and the features available to drive downstream circuits or other instruments that you might want to actually build, such as an electronic load. It consists of two boards, a power board and an actual set of control elements and signal generating elements. Here you can see that I've got it connected up to power. I'm able to provide power through one external route, in this case a power supply, or through a different connector through to a wall wart here. Both of them should provide 15 volts. If the wall wart is powered on, then it overrides anything on this secondary connection here. That just makes sure that only one, there's no competition over power supplies. The power routes in through protection diodes and TVS to prevent any damage from a surge, and there's a power button available which is a master power switch to actually control power to the boards. Power routes through to generate regulated power rails. So we have a 12 volt rail which outputs through this connector here, and that provides power also to an inverter, a 7905 regulator, to provide -5 volts through this connector here. Now I use those -5 volts as a negative supply to the op amps to provide close to rail signalling on those op amps. It provides power into a 7805 regulator to provide +5 volts for most of the ICs that require that on the board, on the control board itself. Power also comes into a DC to DC switching converter, and this is isolated, so there's separation between the incoming power and power that would drive the expensive parts of your circuit, such as your MCU, in this case an Arduino, which might be connected to a PC via a USB connection here or here. And I've taken the choice to provide isolation there so we can protect those expensive bits of circuitry. You'll notice here that there is a placeholder to put in a 3.3 regulator to take that to 5 volts from here down to 3.3, and that would route through to this connector here, which would be connected into this connector here. As you say, no, you should only connect 3.3 or 5 volts, not both at the same time. I'm using 5 volts because I'm driving an Arduino. In this case, it's an Arduino Mega. The red shield is for an LCD that I haven't got attached. The external components on this side is a momentary power switch, which can be used to send an interrupt signal into the board and to drive something that you might want to signal independently of anything else, and for example to power something on or off. Now that I'll show you later how that can route through to your test circuits. There's also a rotary encoder which provides obviously stepped control over values, negative and positive, as well as a push button into the software that you might write on the MCU. It's all routed through these signals, these connectors here. There's also a USB connector which you can plug into your PC that will route to a USB UART chip here, so that you can send serial commands, for example Scupy, or anything that you might want to write on your PC from an application such as LabVIEW or PuTTY, Teraterm, any sort of serial terminal. The jumpers are here to provide control over how you power this chip from the 3.3 supply, if that's what you're doing at this end of the board, or power from the USB connector here, the host. USB UART just routes through RxTX connector on the board here into your MCU. There's a digital isolator here to route digital signals through, and an I2C connector to route the I2C signals through. All the components on this side are generally controlled through I2C. Now I've made the choice, as I said before, to provide that separation. If you're not interested, the board can be set up so that those chips can be done away with, and you could supply the 5 volts from here through cross wiring onto connectors here, and provide the whole lot without having to go through this isolated side if you desire. Looking at the components that are available, we have an EEPROM providing 1 megabit of storage for whatever values that you want to store there. There's a 4.096 reference voltage, and I've provided here a trimmer so that depending on the load you may need to slightly adjust the output voltage. There's a battery backed up RTCC which provides calendar and time, as well as a multifunction pin which can generate a square wave or signal and alarm. Well, there's 2 alarms actually. Battery backed up. There's a fan control, which is just a simple MOSFET, so drive its gate high or low to turn the fan on or off, connected to this connector there to the fan. We have a digital analog controller here to send signals out to your test circuit. 4 channels. You see I've got the silk screen marking wrong, which I've fixed in the latest version of the board. And there's an ADC circuit here. The ADC, this chip here, is actually buffered by an op-amp here, and the components around it are there to manage the signal, to clear the signal, and to provide some over voltage protection. The ADC channel's routing through this connector here. So off board you can drive your instruments or your test circuits with the I2C signals on this connector here, and there's also the multifunction pin, so if you want to generate the alarm signals on or the square wave on, you can do. And there's a power signal here, which is a simple which you could use as a simple high-low switch, perhaps controlled by the power button here, so that you can either turn things on or off, or just generate different behavior on the transition of a high to low waveform. The ADC connectors here, that connectors here, and all the power supplies that you might want routed through this block here. So all in all, you have a number of signals that you can generate in and out to your MCU for controlling your test circuit, as well as a number of power rails to drive it. We mentioned before that you can power the circuit from either one external supply, in this case a PSU, or a wall wart. I've always my preference would be to be driving this through a wall wart, in this case 15 volts, but the option is there to do either, and it might be useful to have a very quiet supply provisioning power, as well as the more noisier supplies, so you can see if there's any impact between using the two. Now the wall wart does take priority, and I'm wondering if we can see that happen. If I position this here in the right place. Sorry, that's not really ideal, is it? When we put power to the board, you can see the power switch light on here. You'll see the initial flashing LEDs over here as the Arduino powers up, and in the background you can see the voltage and current being provided by the PSU. At the moment, no power is supplied to the board, so no current is being drawn. If I turn this on, it will actually provide power through the wall wart. Let me turn the overhead light off, and that hopefully will make it a bit easier to see the lights. So again, there we go. Now if I take this wall wart and disconnect it, you can see that we're now providing 83 milliamps through the PSU. Depending on how quickly you're able to transition that switch, you may find that there is disruption to the board. And trying to operate this one-handed is quite difficult. Let's see if we can do that. Yeah, and you see the PSU has dropped down to 0 amps again. Up. And down. Up and down. So if you can do that transition fast enough, you'll see that the PSU, the MCU didn't actually reboot there, or there will be a slight drop in the power on the power rails there. Okay, so that was just a really quick sort of overview of the board. My next videos I want to use to show it actually working in various ways you could use that.